Okay. Hello, everyone. Welcome to my presentation. And I'm one of the SPIN students. Uh, and so I'm working with these people, and Alice and Heiners are my supervisors. And Dave is helping me with the numerical simulations, while Christoph is helping me with the observations. So the topic of my project is about how can we develop the nonlinear models for modeling the velocity change during the dynamic perturbations of the waves. We have been talked about a lot today and also yesterday. So the very starting point is such kind of observations where we observe the change of the velocity, the drop of the velocity during the damage phase and the slow recovery. Christoph has introduced these kind of things very much, so I not go too much into details. But the thing that I would try to do is to come up with a mathematical model that can describe this phenomenon in the wave propagation simulation and numerical schemes that can solve the nonlinear propagation system rigorously. And the key components of the nonlinear observations is such kind of large time range log scale recovery of the velocities. There have been some pretty nice models. For example, Christoph has also mentioned his work with and that with some superposition of the relaxation at different time scale, they can reproduce the very extended log time scale recovery behavior. But and aside from their model, there have been a couple of models to try to describe the damage and recovery thing during the to describe the rheologies. For example, worth mentioning here is the first model proposed by Christoph, and it is a model that capable of modeling many different experimental observations that Parisa will also going to show in her later talk today. And another very useful model I found is this interval variable model it shows here, which is proposed by Harold Benjamin, who is also here and is going to give his talk tomorrow. So comparing among all these models, there is a common problem that they cannot really consider the account for the log scale recovery that are extensive in a very wide range. So what I did, maybe I should. Yeah. So what I did is to make a little bit change on the interval variable model proposed by Harold, and to get this recover this log timescale recovery. The thing is that now this recovery phase can be coupled with the string variations of the during the wave propagation of the waves, and this is what I did with my numerical simulations. And these kind of the feature here is that the recovery phase can be now taking place at a much longer durations compared to the damage phase. And the reason why I choose this model is also because it has, I think it has the minimum amount of new variables that we need to fit in. It just adds 3 additional parameters to describe this whole non-classical nonlinearities, which means we can more easily to feed the data, feed the experimental observations or in the field to this set of equations. These are one of the numerical simulations that I done with a single frequency sources, and the numerical numerical simulation is done with the discontinuous Gherkin method, and it is implemented in Phoenix, which is the open source finite elements package. And during the propagation of the waves, we can observe as the wave propagated, we observe the attenuation due to damage of the materials. And also what we observe is as the wave propagated further, we can see that the frequencies are shifted to lower values, by recording the time series at these three colorful dots, we'll be able to see it clearly. This is the frequency response at different distances from the sources. We can observe that the frequencies are shifted to lower values. And this is a transient effect that happens during the damage phase of the materials. And the frequency will shift back to the original values after a longer period of time. Aside from that, I'm now also working on trying to extend this code from 1D to 2D, and this is just a very preliminary results. The simulation is not fully verified, so it's just to show this model is also usable in the 2D or 3D cases. And here is I play it again, how the damage has developed in the place where I inject the sources and slowly recovered after the wave says leave the center part. Yes. And some outlook and questions that I posed here to get some response. The first, I would like to compare the modeling with the experiments, because in the experiment is conducted in a more controlled manner, either in sources or the materials. So I would try to compare the experimental observations and try to constrain the model parameters. There are many observations in the lab. There are the strain rate dependence behavior. We also have amplitude dependent damage of the velocities. And another thing is a question I posed here is when the recovery is exponential and when it will be logarithmic, because both are being observed somehow. And another scale is the structure scale, where I will try to cooperate with Markel at the University of Hamburg. They are doing experiments on a bridge. And so I will try to see if I can use the slow dynamic parameters to help do some non-destructive testing. And the final destination will be on the field scale, which is going to be very hard because the field observations is contaminated by different rheologies like the attenuation from scattering or absorption introduced by Ludwig 2 days ago. And just some other questions. The final one would be which part of the Earth where such kind of nonlinearities will be prominent. And that's all, and looking forward to some questions.